Just minutes ago, NASA released something nobody saw coming. The James Webb Space Telescope just looked at a planet that should be dead. A boiling rock, baking for billions of years, so close to its star that its surface should be stripped bare. And yet, it is wrapped in a thick atmosphere. Scientists are stunned. The textbooks are wrong. What you're about to see changes the way we understand rocky worlds forever. Stay until the end. The last part of this story is the part nobody is talking about. Before we get into what just happened, let us take you back to the beginning. Because to understand why this discovery matters so much, you have to understand what a planet like this is supposed to look like. Most people picture planets the way they were taught in school. There is Mercury, the little scorched rock closest to the sun, then Venus, wrapped in its thick blanket of clouds, then Earth, blue and gentle, then Mars, cold and dusty, then Jupiter, Saturn, Uranus, and Neptune, the gas and ice giants, 8 worlds in a nice tidy row. That is the picture we grew up with. For most of human history, that was it. Those were the only planets we knew. We thought we understood the rules. Planets close to a star get hot, planets far from a star get cold. Rocky planets are small and dense. Gas planets are big and fluffy. A planet too close to its star will lose its air. A planet made of rock cannot hold onto a thick, cloudy atmosphere forever when its star is constantly blasting it with radiation. That was the rulebook. We were so sure of those rules that we built entire careers on them. Generations of astronomers spent their lives modeling how atmospheres form and how they get stripped away. They simulated solar winds. They simulated magnetic fields. They simulated the slow boil of gases off a planet's surface as its star heats them. Those simulations worked for our own solar system. They worked for Mercury. They worked for the Moon. They worked for every dry, airless rock we had ever touched. Then in the 1990s, the first exoplanets were discovered. Worlds orbiting other stars, hundreds of them, then thousands. Today, we know of more than 6,000 confirmed exoplanets, and the number keeps climbing. And almost every single one of them broke the old rules in some way. There are planets the size of Jupiter that orbit their stars in just 2 or 3 days. There are planets bigger than Earth, but smaller than Neptune that should not exist according to the old models. There are planets so hot, they rain iron. There are planets so puffy, they have the density of cotton candy. The universe, it turns out, is far stranger than the solar system alone ever suggested, which brings us to the telescope that just rewrote another rule, the James Webb Space Telescope. Webb is the most powerful eye humanity has ever pointed at the sky. It sits about 1 million miles from Earth, parked on the cold, dark side of a special gravitational balance point, where it can stare into space without being blinded by our own sun. It is bigger than a tennis court when unfolded. It carries a giant golden mirror made of 18 hexagons that capture light no human eye could see. It sees in infrared, which means it can see through dust, through gas, through the dimmest corners of the universe. Webb was launched in 2021, and within months, it started changing everything. It took pictures of galaxies that formed only a few 100 million years after the Big Bang. It studied the atmospheres of exoplanets and detected carbon dioxide for the first time. It looked at baby stars being born inside huge pillars of dust and gas. It captured pictures of Jupiter and Saturn in new colors. It showed us the universe with a clarity that no earlier telescope could match. But there was one thing everybody really wanted Webb to do. From the moment it was launched, scientists had been begging for time on it to study one particular kind of object. Not the bright galaxies, not the shimmering nebulae, the small, dark, rocky planets, the ones that orbit close to their stars, the ones whose surfaces are so hot they glow like the inside of a furnace, the lava worlds. Because those worlds were supposed to be the easiest to understand, their stars should have burned off all of their air long ago. Their surfaces should be cracked and dry and dead. They should look like Mercury times 10, nothing more. Let us say that more clearly. The rule was simple. If a planet is rocky, and if it is small, and if it orbits very close to its star, then its star should have stripped its atmosphere away. The radiation pressure from the star blows on the gas like wind on sand. Over millions of years, the gas drifts out into space. The rock that is left behind is bare. That was the prediction for every such world. That was the rule that every textbook agreed on, until now. Now, in 2025, the James Webb Space Telescope looked at one of those worlds in incredible detail. Its name is TOI 561b, and what Webb saw has every planetary scientist on the planet taking a deep breath. Let us walk you through this discovery piece by piece, because the story builds in a way that even surprised the people doing the research. It started with a planet hunter called TESS. The Transiting Exoplanet Survey Satellite, which is run by NASA, scans the sky looking for tiny dips in the light of distant stars. When a planet passes in front of its star, the star gets slightly dimmer for a few hours. That dip is how we find most exoplanets. TESS had been running for years, and a few years back, it spotted a dip coming from a star we now call TOI 561. That meant there was a planet there. The data showed it was small and dense. somewhere between the size of Earth and the size of Neptune. It was given the name TOI 561b. Follow-up measurements from ground-based telescopes confirmed more details. TOI 561b orbits extremely close to its star, so close that it completes a full orbit in less than 11 hours. That is faster than a single workday. The planet is whipping around its star like a dog on a short chain. Its day side, the side that always faces the star, bakes constantly. The temperature on that side runs around 2,900 Kelvin. That is hot enough to melt rock. That is hot enough to vaporize metal. That is the temperature of a small star, sustained forever. This kind of planet is called an ultra-short-period planet. They are rare, and the ones we have found before looked pretty similar. They are mostly small, dense, and dry. They look like big Mercuries. Most researchers assumed they should have no atmosphere at all, because the radiation from their stars should have literally blown any gas away into space billions of years ago. That was the prediction. That was what models said. That was what every other ultra-short-period planet we had studied had confirmed. They all looked bare. They all looked dead. They all looked like what every model predicted. So when a team of scientists led by Johanna Teskey, a planetary scientist at the Carnegie Institution for Science, scheduled time on the James Webb Space Telescope to study TOI 561b, nobody really expected to find something dramatic. They were hoping to confirm the prediction. They wanted to see how bare and dry this little world really was. They pointed Webb's near-infrared spectrograph, one of its most sensitive instruments, at the planet and waited for the light to come back. What came back changed the conversation. But let us slow down for a moment, because the way Webb studies an exoplanet is itself a kind of magic, and it is worth understanding before we get to the punchline. When a planet passes behind its star, which astronomers call a secondary eclipse, the light we see from that direction momentarily drops. The amount it drops tells us exactly how much light the planet itself was contributing. By comparing the light just before the planet vanishes to the light just after it reappears, scientists can isolate the planet's own glow. That glow carries a fingerprint of whatever gases are floating in the planet's atmosphere. Different gases absorb different colors of infrared light. Water vapor absorbs in one set of wavelengths. Carbon dioxide absorbs in another, methane in another. Silicon dioxide, which is essentially rock vapor, absorbs in yet another. When Webb sees a dip in the planet's light at a specific wavelength, that is the signature of a specific molecule high up in the sky. You can think of it like this. Imagine you're standing in a dark room and somebody shines a flashlight through a glass of colored liquid. If the liquid is red, the light comes out redder. If the liquid is blue, the light comes out bluer. The colors that come out the other side tell you exactly what was in the glass. Webb does the same trick with starlight. The colors of light that come through a planet's atmosphere, or that are blocked by it, tell us what gases are floating up there. So when the team looked at TOI 561b's dayside spectrum, they were looking for those dips. They were looking for the chemical fingerprint of an atmosphere. And here is where the story turns. The data did not show a dead, dry world. It did not show the bare rock signature that every other ultra-short period planet had shown so far. It showed something thick, something layered, something with weight. The spectrum of TOI 561b pointed to an atmosphere rich in volatiles. Volatiles is a fancy word for chemicals that turn into gas easily. The signature looked most consistent with water vapor, oxygen, and carbon dioxide, all hanging together in a substantial envelope above the planetary surface. Not a thin wisp of vapor, a real thick, heavy atmosphere. In other words, this planet is wearing a blanket in a furnace, and that blanket has somehow survived for billions of years. Now, to be clear, this does not mean there is rain on TOI 561b. The dayside is so hot that any water would be a superheated vapor clinging to a sky made partly of glowing rock. The surface, if it even has a solid surface, is almost certainly a global magma ocean. But the gas above it is real. It is dense. It is measured. This is the moment when every scientist on the team sat back and stared. Here is the rule that just broke. A rocky planet of this size, orbiting this close to this kind of star, should have had its entire atmosphere stripped away long ago. Physics says so. Solar radiation pushes gas molecules outward. Over billions of years, it should strip everything clean, leaving nothing behind but bare rock. That is what was predicted for every ultra-short period planet we have ever studied. That is what we see on Mercury. That is what we expect when a world sits that close to a star. Yet TOI 561b has an atmosphere. A thick one. How? That is the question now echoing through conference calls and lab meetings and quiet conversations at observatories around the world. There are a few possible explanations. None of them is fully satisfying. All of them are exciting. The first possibility is that the atmosphere we are seeing is being generated continuously, by volcanic activity, by the boiling of the global magma ocean itself. The day side of this planet is so hot that its rocky surface is essentially a sea of liquid lava. If that lava is constantly outgassing, if it is constantly burping up volatiles, then the atmosphere is not ancient. It is being made fresh every day. It is a thin equilibrium, a constant balance between production at the surface and stripping by the star. That would be wild because it would mean this planet is geologically hyperactive in a way that we rarely see, even in our own solar system. It would mean the rock itself is fighting back against the radiation. The second possibility is something even stranger. Maybe the atmosphere is being sustained by the planet itself, by the minerals inside the rock interacting with the heat and producing gas as a kind of chemical factory. Maybe the rock is reacting with the starlight, the way sunlight can slowly break down chemicals over time. Maybe TOI 561b is essentially a chemistry lab in the sky, cooking up its own weather from scratch. Maybe every square meter of its surface is constantly making gas, and the gas rises, and the gas is stripped, and the rock makes more gas. A cycle, a furnace metabolism, a kind of planetary breathing. The third possibility is the most uncomfortable. Maybe our understanding of how atmospheres are stripped away is simply wrong. Maybe the models that have guided planetary science for decades are missing something. Maybe TOI 561b is showing us a kind of atmospheric protection we did not know existed. Some kind of magnetic field, some kind of internal pressure, some kind of layer we did not realize was possible. The third possibility is the one that worries and excites people in equal measure. Because if it is true, then every prediction we ever made about rocky exoplanets has been wrong. Every other world we looked at and called bare, every Mercury-like sphere we ignored, every thin atmosphere we wrote off, suddenly becomes a question mark again. And there is one more strange detail in the TOI 561b story that has everybody whispering. The star this planet orbits is unusually old. It is roughly twice as old as our own sun, and it is iron poor, which means it formed in a part of the galaxy where heavy elements were scarce at the time. That is important because most of the rocky planets we have studied, including Earth, are made of stuff that includes a lot of iron. The fact that this planet orbits a star with less iron than usual, and yet still has an iron-poor composition itself, is a clue that the planet was built out of unusual ingredients. Somehow, in this strange ancient environment with weak raw materials, this world still hangs on to a thick, volatile, rich atmosphere. The deeper you dig into this discovery, the more wrong every assumption looks. There is another piece to this that has stirred up even more discussion among the science teams. The density of TOI 561b is unusually low for a rocky planet of its size. Most rocky planets, smaller than Neptune, are squashed and dense, packed with iron and heavy minerals. TOI 561b is 4.3 grams per cubic centimeter. That is lighter than Earth. That suggests it is holding more gas than its mass should allow, in a way that models struggle to explain. It suggests the atmosphere is heavier than we thought, or that the rocky core itself is unusually porous, gassy, or strangely composed. This is part of why this discovery has hit the science community so hard. It is not just one anomaly. It is a pile of them, stacked one on top of another, a thick atmosphere where there should be none, a low density where there should be heavy rock, a volatile rich chemistry where there should be dryness, an ancient iron-poor star, supporting a planet that should have been stripped bare. Every piece of the puzzle embarrasses the models in its own way. But here is where things take a strange turn. You would think that the most striking part of this discovery would be the size of the atmosphere itself, the sheer audacity of a rocky planet hanging onto gas for billions of years in a furnace. And yes, that is shocking. But when the team started running their models, something else started to bother them. The atmosphere did not just exist. It was the wrong shape. Most ultra-short period planets we know about are tidally locked. That means one side always faces the star, like the moon always shows the same face to Earth. The day side bakes, the night side freezes. The atmosphere, if there is any atmosphere, usually moves heat around in a predictable way. Hot air rises on the day side, drifts to the night side, cools, sinks, drifts back. But TOI 561b's day side spectrum does not look like a tidally locked world with a normal heat cycle. It looks chaotic. The brightness profile is uneven. Some regions seem hotter than they should. Some regions seem cooler. The simplest explanation is that the atmosphere is moving heat around in a way our models do not predict. It could mean the winds are extreme. It could mean the atmosphere is layered in ways we did not expect. It could mean there are convection cells far larger than anything we have modeled on a rocky planet. That is the kind of detail that drives researchers back to their computers at midnight. Another unusual clue came from the planet's overall brightness. The total amount of light Webb measured from TOI 561b was higher than expected. If the planet really were a bare rock, it should have reflected and emitted a certain small amount of light. Instead, it appears to be giving off more light than a bare rock would, consistent with an extra layer of something above the surface. That extra layer is what the team is interpreting as an atmosphere. But here is something the press releases did not emphasize. The team had to choose between several different atmospheric models before they got one that fit. They considered a pure rock vapor atmosphere, where the atmosphere is essentially made of vaporized minerals. They considered a thin hydrogen-dominated envelope. They considered a thick, volatile-rich envelope. The thick, volatile-rich envelope won, but only by a margin. The science here is not slam dunk. It is the best fit currently available. That does not make it wrong. It makes it provisional. And provisional science is the most dangerous kind, because it is the kind that gets either confirmed beautifully or overturned completely in the next round of observations. That is why follow-up is so important. And follow-up is already being planned. So how are the experts reacting? Honestly, with a mixture of caution and wonder. The lead author, Johanna Teske of the Carnegie Institution, has been careful in her public statements. She says this is the strongest evidence yet that a rocky planet outside our solar system can hold on to a thick atmosphere under extreme heat. She reminds everyone that more observations are needed. She wants to confirm what Webb is seeing with other instruments. She wants to compare the dayside measurement with the nightside. She wants to see if the atmosphere changes during the planet's very rapid orbit. In the wider community, reactions have split into two camps. The first camp thinks this is fascinating, but probably has a relatively boring explanation. Maybe the atmosphere is thinner than it looks. Maybe the model fit is not as strong as the headlines suggest. Maybe follow-up observations will tone it down. These researchers keep reminding the public that atmosphere detection on rocky exoplanets is famously tricky. There have been false alarms before. There have been signals that look like water and turned out to be stellar contamination. There have been methane detections that collapsed on second look. Skepticism is healthy. The second camp thinks this is the real thing. They think Webb has finally caught a rocky planet doing something we did not think was possible. They think the textbooks really do need to be updated. They think we're looking at a new kind of planet, a new category of world, a member of a class of objects we did not know existed. They point out that Webb has been right far more often than it has been wrong in the exoplanet field, and that its sensitivity is far beyond anything we had before. Both camps agree on one thing. They agree that James Webb has changed the field again. There has been no shortage of debate. Some researchers have pointed out that the spectral signatures could be partly explained by clouds of silicate particles, essentially tiny droplets of vaporized rock floating in the upper atmosphere. That kind of cloud layer can produce a similar pattern in the data without requiring a thick gas envelope of water and carbon dioxide. That is a valid concern. But the team's modeling suggests the volatile-rich atmosphere explanation fits the data better than the pure rock vapor explanation. Other researchers have noted that Webb's measurement was taken at a single moment in the planet's orbit. It only saw the day side glowing in infrared. The night side could be very different. The atmosphere could be condensing on the dark side, raining down and being recycled. We just do not know yet. The follow-up programs will look at the full orbit. They will watch how the planet's brightness changes as it spins, as different sides come into view. That is, when the real picture will come into focus. Another angle that has come up in private conversations among the senior researchers is this. If TOI 561b can hold an atmosphere, what about other ultra-short period planets in the same neighborhood of parameter space? Are there dozens more out there wearing invisible cloaks? Are we about to discover an entire new family of worlds? That would be a turning point for exoplanet science. That would mean the planets we have ignored for decades, the ones we wrote off as small and uninteresting, were holding secrets we were too quick to dismiss. And there's a long tail of implications. If rocky planets can hold atmospheres in extreme environments, then the habitable zone around stars might be bigger than we thought. The traditional habitable zone is the band of orbital distances, where temperatures allow liquid water on the surface. It is the region where Earth sits, where Mars sits at the cold edge, where Venus sits at the hot edge. If planets outside that traditional zone can still keep atmospheres and chemistry and complexity, then the number of potentially interesting worlds in the galaxy just got bigger. That does not mean TOI 561b itself is habitable. It is not. Its day side is molten rock. Its night side, if it even rotates, is freezing. The chemistry in its atmosphere is exotic. But the principle that it proves, the idea that rocky worlds can hold on to complexity in extreme conditions, that principle ripples outward to every other world we have ever looked at. It is also worth saying that this is not the first time James Webb has surprised us with an exoplanet. A few years ago, Webb studied WASP 39b, a giant puffy gas planet, and detected carbon dioxide in its atmosphere for the first time ever. Then it found sulfur dioxide, a chemical produced by photochemistry in the upper atmosphere. Then it found water in clouds and sodium and potassium. Each observation revealed that these distant worlds were more chemically rich and more complex than people had expected. But those discoveries were about gas giants. Gas giants are easier. They are big and bright and full of hydrogen and helium. They almost always have thick atmospheres. The expectation is built in. Nobody was shocked that WASP 39b had air. TOI 561b is different. It is small. It is rocky. It is the kind of object we expected to be dry and dead. And now it has air. That is the shock. That is the rule that broke. It is also why this discovery is being talked about in almost reverent tones in planetary science circles right now. There is a real sense that we are watching a paradigm shift in real time. Less dramatic than a movie moment, but just as profound in its own quiet way. There is a personal detail in this story that I cannot skip over. The lead author of the paper, Johanna Teske, has been working on exoplanet characterization for a long time. She cut her teeth on the early spectroscopic work of the 2000s and 2010s. She has spent years watching the field inch forward, model by model, observation by observation. When she talks about this result, even in her careful scientific language, you can hear something else underneath. You can hear the feeling of seeing something nobody else has seen. That is part of what makes space science feel alive.